Okay, so for part 1 of the Unit 1-5, this is the final section of notes here in Unit 1, and notice it's Chapter 2.6 if you want to check your book at all. I had the students in class, I had them conduct a lab to find the acceleration due to gravity by using a ball on a ramp. So just breaking down and reviewing this a little bit. We talked about this situation a lot last year, right? We know that if an object is on an incline like this, the only force naturally acting on it is the acceleration due to gravity, the force due to gravity, that's pulling it straight down. And the significance of that is the acceleration pulls straight down, but then there's a component of that acceleration that pulls perpendicular to the ramp, and there's a component that pulls parallel to the ramp, such that we have a right triangle, where this is our right angle over here. So the idea was, if you can find the acceleration down the ramp, so I had the students do that through a lab, was measure the acceleration going down the ramp, and then work backwards to build this triangle. Just to review some of those basics real quick, right, we need to make sure we're comfortable with the fact that whatever the angle the incline makes down here with the ramp, let's say this is theta, if that angle is theta, then this would be a right angle, so this would be 90 minus theta, which would then mean this angle again is just theta. Okay, so if I ever want to find the acceleration down the ramp, it's just my gravity, which would be the hypotenuse of this triangle, times the sine component of theta. So the acceleration down the ramp equals gravity times the sine component of theta. And obviously always make sure you're in degrees and not radians when you're doing this, but otherwise just make sure you're comfortable with this context, right? So make sure you're comfortable with things accelerating down a ramp. If you are, you can measure the time, the distance, whatever you need to do. Okay, so I wanted to start then with an example that kind of had us do that. So just a little bit of background. A photogate is a device, we've seen it referenced a few times going back to multiple choice questions, but it's a device that will measure an object's speed as it passes through its field of vision. Okay, so basically it just measures the speed as it's passing through its lens there. So anyway, a photogate is used for this lab. So in a laboratory, a 2-meter long track has been inclined 20 centimeters off the ground with 180 centimeters displacement horizontally. So what that's saying is our ramp looks something more or less like this, where we've got 20 centimeters off the ground here, or 0.2 meters, and then 1.8 meters horizontally long. So obviously that then gives me a chance to find my angle. Right, that gives me a chance to find my theta. Okay, so we'll see if and when we need that to come up shortly here. But anyway, you place a photogate every 30 centimeters from a line you've marked near the top. So you place a photogate at every one of those centimeters, and then you generate the following data. So based on the photogates, obviously at 0 we know it was started from rest, so it was at 0. And then at 30 centimeters we found the speed to be 0.75 meters per second, 60, 1.15, and so on and so forth. So then I ask you, just kind of generically, use a graph and equations to interpret this data and help you find the acceleration due to gravity. So the first graph that I want us to make here is, let's go ahead and make a velocity versus displacement graph. So think of this as my x-axis, think of this as my y-axis, and let's see what that looks like. And so feel free to pause if you need to, but go ahead and sketch that graph, and I'm going to scroll down. I've already made mine. So I'm doing, again, a velocity versus displacement graph. So I plotted my points, and obviously yours might be a little bit more accurate than mine. I tried to do this about as best I could in terms of spacing and everything. But I do want you to notice, right? So looking at this graph, it does look like there's maybe a slight curvature to it, right? It doesn't look like it's just a straight line. It looks more like maybe it's a curved function that goes something more or less like that, as opposed to just a linear equation that goes straight through. So I want you to think about, so what does that mean for this graph? Right? Well, if the slope is changing, what does that tell us? But be careful, right? What is this graph illustrating? This graph's not showing me velocity versus time. It's showing me velocity versus displacement. So the reason I say I want you to pause for a second and think about that is because what does this slope actually mean? Well, this slope would be velocity, it'd be my change in y, so my change in velocity over my change in x, which would be change in x. So I'd have meters per second divided by meters, which would cancel out the meters. I'd end up with per seconds. So what does this slope actually mean? All right, well, per seconds are actually what we measured as hertz. It's actually a measurement of frequency, but that doesn't really make a whole lot of sense in any type of motion that's not periodic. So the slope for this graph has no meaning. So this graph doesn't really make sense to represent our data because it's not showing me anything meaningful. So instead I want you to think, what's the function, what's the relationship that relates velocity to displacement? Well, instead of using just something like VOTAT, right, because VOTAT would relate the velocity to the time, instead if I use v squared equals v sub 0 squared plus 2a delta x, that's the actual relationship I want. And this takes us back to something we saw last year, and that something was what we referred to as linearizing the curve. If you want to make this graph to where the slope is actually meaningful, you want to make this graph into maybe a linear function representing these variables. So linear functions, we know, typically take the form of y equals mx plus b. I'm actually going to write that as b plus mx, and you'll see why in just a second. Okay, but if I want to linearize this curve, rather than plotting velocity versus displacement, I'm actually going to plot velocity squared as my y value. I'm still just going to use displacement as my x value. B would indicate, obviously, then my starting velocity squared. So my y-intercept would tell me what the square of my initial velocity is. And then the big key here is when I do velocity squared versus displacement, my slope is going to be 2 times the acceleration. So it does have meaning if I plot velocity squared versus displacement. Now the other alternative you could have done, you can definitely do this as well, you could just take the square root of everything, right? So you could plot v versus the square root of v sub 0 squared plus 2a delta x. So in other words, you could plot it against the square root of delta x, but that makes it a little tougher to see what the slope is. So I actually would prefer to just do this one. Okay, so take a second, calculate your squares of your velocity, and then we're going to replot this. So I'm going to go ahead and scroll back up here real quick. Again, calculating these values, and you guys can do this for yourselves, but I'll write these in as well. So I'm just squaring each one of these values so I have them to work with, and obviously you can round them off to a few places here. I'm going to go ahead and write them out to a few places as well. But you could round these off wherever needed to be. And I don't know why, but I think I rounded that last one off just for fun. Okay, so anyway, rather than plotting velocity versus displacement, I'm going to plot my velocity squared versus displacement. So then I've done that graph as well. You guys can take a second to do so too. But what I want you to notice about this graph is, looking at that graph, it definitely follows a linear curve, right? If I go from here to here, it's definitely more or less a straight line. Now a few of those data points, and it's okay if they deviate a little bit, because these data did come from actual measurements in the lab, so they shouldn't be a perfect straight line. And obviously my graph has probably some inaccuracies as well, but it's fairly close to a straight line, right? So the significance of this again is when I do my velocity squared versus my displacement, I actually have meaning. Okay, so if I asked you to use this graph or this data to find the acceleration due to gravity, what we could do then is say, well, the slope of this line, which we can now pretty easily calculate, the slope of this line again equals 2 times the acceleration down the ramp. So then if I wanted to find my acceleration down the ramp, that would just obviously be m divided by 2. So whatever half of this slope is, that would be the acceleration down the ramp. Now keep in mind, that does not mean that's my gravity. That simply means it's my acceleration down the ramp. So if I go back to my ramp, which was 0.2 meters tall and 1.8 meters long, what I've found by using the slope is the acceleration going this way, which can help me to find the acceleration due to gravity because I know, again, that's the sine component of gravity. Okay, so you can do the math here, do the calculations if you would like, but the big goal that I want you to be comfortable with is, one, reviewing the velocity versus the displacement as a function, and then how we linearize various functions. So we'll see this a few times throughout the year. Definitely something to get some practice with, and definitely something I expect you to know. Something that you should be comfortable with. If I give you various forms of data, finding a way to represent that has a meaningful slope is always something we should try to do. So anyway, spend some time finishing out the calculations here if you would like to, reflecting back through this and making sure everything makes sense. If it does not make sense, please let me know so we can talk about it a little bit more. Okay, so reviewing briefly turning points. I know I've spoken with a couple of you already about the turning points, but it doesn't hurt to see it again. Okay, so if a question asks us to find the turning point, there's a couple different ways we can do it. The first way is if I know the velocity function, right? So if I give you some velocity function and ask you to find the turning point, then the turning point simply comes from where does the velocity function equal 0 with one condition. And that condition is, in order for the object to turn around, the velocity has to go from either positive to negative or from negative to positive. So the velocity function does have to equal 0, but more importantly, it actually has to change directions before and after 0 as well. What I mean by that is, and sometimes it's easier to represent this graphically, and obviously if I gave you a velocity function, if I gave you something like this, you guys have TI-83s and 84s and 89s, you can always just plot these and see what happens as well. But if I gave you a function like this, to where it was a velocity function, it came down here and it touched 0. So it had one intercept right there down at 0. And I asked you, is that a turning point or not? The actual answer for that would be no, right? Because the velocity all the way down to that point is still positive. Yes, it's decreasing, it's slowing down, slowing down, slowing down, slowing down. Then it's 0 momentarily, but then it picks up speed in the positive direction. So it's moving in the positive direction this whole time, and then it continues to move in the positive direction. That does not turn around, so this is not a turning point, right? That is not a turning point because it doesn't actually cross through the x-axis. However, right, if I give you a velocity function something like this, then each of those locations where, again, this is velocity versus time, each of those locations where it actually passes through the x-axis, that would be a turning point. Because here I go from a positive velocity to a negative, and then from a negative velocity to a positive. Okay, so be careful on this. Again, the easiest thing you can do a lot of times is just graph the function and look at your values. And make sure on your graphing calculator you're comfortable finding like a 0 or something of that nature. If I gave you a position versus time graph, how could we find the velocity function? So let's say maybe I give you a position versus time graph that looks something more or less like that. How can I find the turning points? Well, again, the turning points would actually in this case be anytime the velocity changes from positive to negative or vice versa. So anytime the slope changes from positive to negative. So basically, truly, just anytime the graph turns around. So this would be a turning point, this down here would be a turning point, and this down here would be a turning point. So anytime that we have a minimum or a maximum, we would have a turning point. Again, something to watch out for though would be if I gave you a position versus time graph that looks something more or less like this, even if its slope is momentarily 0, if it doesn't actually turn around, that would not be a turning point. So watch out for little details like that. Algebraically, you can solve for the turning points by plugging for 0 and then checking. But again, graphically or even just algebraically and plugging in numbers, you need to be sure that it actually changes sign in order for us to know for sure that it is a turning point. So make sure you're thinking about that. What about on an acceleration versus time graph? So what if I gave you an acceleration versus time graph that did something more or less like this? How do we know if it's a turning point or not? Well, how do we determine the velocity from an acceleration versus time graph? Right? The velocity would be the area underneath the curve. So my change in velocity would be the area enclosed underneath any curve, right? Where this would be a positive change in velocity and this would be a negative change in velocity. Well, in order to know the turning point, right, we need to know that the velocity goes from being a positive number to the velocity being a negative number. So based on this graph alone, I actually would not be able to find the turning point. Because even if I knew that the velocity went negative, I'd need to know what the initial velocity is. And how do I know the initial velocity? By just looking at this graph? I don't. I know the change in velocity, but I don't know the initial velocity. So if they just gave us a velocity, or excuse me, if they just gave us an acceleration versus time graph, you actually don't have any immediate ways of finding the turning point. What I would recommend instead would be, because we have the acceleration and we can represent it as a function, let's do the integral of the acceleration to find the velocity function, and then just use the graph or the equation for this to find your turning points. So spend a little time thinking about that. Again, if you do have further questions on any of this stuff, I know this is some of the trickier stuff to understand, particularly just watching these videos. We will see a couple examples as well, but don't hesitate to let me know if any of this is not setting in. And we'll see through some practice if it is or isn't.